So it is a pleasure to present you David Loeffler. He from Warwick University. He's going to give the first of three lectures, a mini course that is given David Loeffler and Sarah Zerbes. And the title is p-adic function via higher Hida-Coleman theory.
Well, thank you very much for the introduction, and it's an honor to speak here, and in particular to speak after this wonderful lecture series by George and Vincent. So I hope I can maybe try and keep up to the standard they've set a little bit. So the aim of this of these lectures is to explain some applications of higher Hida theory to constructing p-adic L functions, and really the theme here is the interaction of higher Hida theory and HidaColeman theory on different groups. So let me start by talking a little about L functions of Siegel modular forms. So I want to take pi to be a cohomological automorphic representation of GSp4. And as we saw at the end of Vincent's talk a moment ago, this has somehow a local system weight, which is the weight of the local system whose cohomology it contributes to. And that's a pair of integers, R1, R2, R1, at least R2, at least 0. And then it contributes to the cohomology of many coherent sheaves. So if xg is the compactified Siegel variety, some large enough level, we get several sheaves on this. We have sheaves omega k1, k2, with k1, at least k2 integers. And there are several of these, 4 of these in general, to whose cohomology pi will contribute. So pi appears in H0 of xg omega k1, k2, 1, k2 equals R1 plus 3, R2 plus 3. And these numbers aren't so important. I'm just writing down explicitly the slightly shifted action of a Weyl group that was appearing in the previous lectures. And there's some other formula here. And these are all in different Weyl chambers. And let's call these sheaves. N0 up to N3. So it contributes to H0 of N3, H1 of N2, etc. I've numbered them this way round because then they naturally form a complex. So what we want to study is if pi, so what was I? So pi gives rise to an L function, L pi s, which has some critical values. I'm going to shift them so the critical values start at 0 and it goes up to R1 minus R2. This isn't the usual analytic normalization, but it's the simplest one here. And we want to use these coherent cohomology groups and the goal is to build.
Sorry, David, which L function are you talking about?
Sorry, I should say this is the degree 4 L function. what people call the spinor L function. There's also a standard L function of degree 5, and that's the one I'm not going to be using. But this one is important here because it's the one that corresponds to the Galois representations, which appear in the cohomology of the Siegel modular variety. So yeah, so it's the degree 4 L function. So we want to build a p-adic L function interpolating the values over some suitable period in this critical range. So I apologize, it's there's no easy way of me putting 2 pages on the screen at once here, so you'll have to remember what I just wrote, I'm afraid. And one reason this is difficult, it seems to be hard to do this using the holomorphic Siegel form. So the guy in H0, or its complex conjugate, which gives you something in H3. You really need the middle degree things. And there's somehow an explanation for this in terms of Archimedean representation theory, which is the holomorphic discrete series of GSp4 is not generic. But on the other hand, if you use the middle degree guys, the pi eigenspaces in H1 and H2, you can get somewhere. The theorem, this is due to Piatetsky-Shapiro. Piatetsky-Shapiro proved this up to identifying what the Archimedean term in the integrals was, and then that was evaluated much later by Moriyama. So we take phi pi to be some C infinity automorphic form contributing to H2 in the pi eigenspace, then you can integrate over a certain subgroup So I'm just going to write out a formula and I'll tell you in a moment what the notation means. So there's this rather pretty formula. And now let me define the terms involved. So H is the subgroup GL2, 5 product over GL1, GL2. So just pairs of matrices with the same determinant. And we're embedding that into GSp4 as matrices that look like this. So that's the map iota, and it gives you a map on the symmetric spaces. And the final piece of the puzzle is that the EI are GL2 Eisenstein series. So these are real analytic things depending on a parameter. But you can arrange that for S critical, or more accurately for these combinations being critical, these are in these are holomorphic, or nearly holomorphic forms. I'm not going to say too much about the nearly holomorphic side of this story, but it is there. But for now, just imagine you're at one of the extreme ends of the critical range, and then these are both holomorphic Eisenstein series. So the important thing is that this fudge factor here is not 0. Because there's a bit of choice in how you choose the Eisenstein series and exactly which local test vectors you choose at the finite places here, but you can choose them in such a way that the fudge factor is not 0. And we want to interpret this as something cohomological that we can kind of drag into the world of algebraic geometry. And it was worked out how to do this by Harris. So phi pi gives a class eta pi So this is just the cuspal version of the sheaf with the boundary divisor there. And you can also consider the push forward of the Eisenstein classes, the Eisenstein series, I should say. So these are classes in an H0, and when you push them forward, you get something in an H1. And this sheaf is the Serre dual of this one. And so we can identify the L value as the Serre duality pairing.
I'm sorry, David. We
Oh, sorry.
see. Oh, yeah. Thanks.
Thank you. So this has all sorts of nice consequences in itself. It tells you that if you scale this guy so it's defined over a number field, then the pairing that comes out will be defined over a number field. So you get an algebraicity statement for the L values. Divided by a period, and that period is coming from the Whittaker model. So this comes back to what I was saying about it being impossible to do this sort of thing with holomorphic forms, because the period is really a period coming from an H2 here, and the holomorphic forms are somehow really not seeing that period. And here's the question. If we move, the EI in p-adic families, do these products vary p-adically? So that's really the question we need to answer in order to construct p-adic L functions. And it also has lots of other nice applications, for instance, to Gross-Prasad type period problems for restrictions of cusp forms and so on. But this is really the application we care about here. And we wanted to understand these p-adic L functions motivated by applications to Euler systems, which Sarah is going to talk about in her lecture. And that is really where the higher Hida theory comes in. And the tool we're going to use to attack this is higher Hida theory for Klingon levels. So this is somehow a slightly less powerful p-adic theory of interpolation, in that you can only vary one of the two components of the weight. But it turns out to be enough for these applications, and it's in many ways technically simpler. And it was discovered earlier. So this was the first thing we found out about from Van Sant and used in this project. So this also came up in Fabrizio's talk. So I'm going to take the Klingon parabolic, which is the things in my group that look like this. And all the rest are zeros. So I have the parabolic subgroup, the algebraic group, and the associated parahoric subgroup. And I'm going to take a chamorro variety X Klingon, and it's going to have some level away from P, which I don't care about very much. And it will be Klingon mod P. And this is a moduli space for pairs AC, where A is an abelian surf. I mean, this is the uncompactified chamorro variety. I'm not going to be precise about what happens at the boundary, but this is the idea. So the level structure at P, again, there's some polarization and prime to P level structure, which I'm not writing, but the crucial thing is there's a level P subgroup. I'm going to draw a picture of this variety, which is kind of rather, possibly rather misleading picture. So it has two big blobs. So this is the locus where C is multiplicative. Here is where C is étale. And there's some stuff in the middle where C mod P is alpha P, the biconnected group scheme over FP bar. And this is slightly bad notation, but it seems to have become somewhat standard nonetheless. I'm going to call this bit X Klingon greater than or equal to 1. So this really ought to signify the locus where the P rank is at least 1, which is in fact this together with this. But I'm actually taking somehow the good component of it. I'm taking the good component of the multiplicative locus. So the idea is to study just the cohomology of these sheaves omega K1, K2 over the greater than or equal to 1 locus.
Sorry, David, maybe you can.
Oh yeah, I've got it. Yeah.
Thanks.
Because I turned the camera around and now it's focusing on a very small space. and we want to consider this guy, and we want to consider what you might call the Klingon ordinary part, where E Klingon is the ordinary projector for the Hecker operator p squared p p1. So notice this is not a dominant co-character. It's somehow dominant relatively to the Klingon, but not for the Borel, because the power of p doesn't jump in this middle block. So it's somehow the Hecker operator associated to the Klingon. And the theorem, which is worked out in our paper, but is mostly a fairly straightforward generalization of the statements in Van Sant's earlier paper, where he was focusing on non-regular weights. Oh, I should have said there's a condition on K1 and K2. So we want K2 less than or equal to 0, K1 plus K2 at least 4. So this is one of the regions that was drawn on the diagrams of weights earlier. So this is almost the region where classically you'd expect to have an H1. But there you have to throw away the K2 equals 1 line, which this theorem ought to cover but doesn't, because the methods are slightly suboptimal. So you get a finite free ZP module in rank 1, in degree 1 only, and the cohomology in all the other degrees is 0. And 2, this guy is isomorphic to the classical cohomology, so the restriction from the cohomology of this whole blob to just this part over here induces an isomorphism on the Klingon small slope part.
I'm sorry, David. Oh, okay, we didn't see the last line of the previous page. Oh, perfect. Thanks.
You good now?
Thanks.
Yeah, so one would have a similar statement if you took K2 positive and bigger than 3, but then you'd have a complex concentrated in degree 0. And in Van Sant's previous paper, he studied the case where K2 was 2, and then you had a complex that somehow equally spread between degrees 0 and 1. But in this range, it's concentrated entirely in degree 1. So this does actually vary analytically in families. In K1 for fixed K2, but we're not going to use this. It's not vital to the construction of the p-adic L function. So I'm not going to say anything about the proofs here. So this is, as I said, very similar to the argument in Van Sant's Duke paper, and the the parts that are different are sketched in our recent preprint, but I'm sure that you'll believe these statements, having seen the much more sophisticated and powerful generalizations in the lecture courses elsewhere in this workshop. So now I want to get down to the main new thing here, which is the question, what happens when you compare this to classical Hida theory on H? So what am I up to? 3. So what we want to do is to find some sort of push forward map, some sort of version of iota lower star which should go from pairs of p-adic modular forms to H1 of the complex I described above. And the important thing here is to work out exactly what you mean by iota in this setup. So there's several ways to embed a chamorro variety for H in X Klinger. So I'm not so interested in the story away from P, but the important question is, how does the level structure that this thing is parameterizing interact with the subgroup H? So we have a pair of elliptic curves E1, E2. So if we have C a subgroup of the abelian surface E1 plus E2, there's 3 possibilities. We can have C inside the p torsion of E1. We can have C inside the p torsion of E2, or, and this is the less obvious and more subtle possibility, C projects isomorphically in E1 or E2. And that means you get the subgroup CI inside the EI, but you get one tiny extra piece of information. Because these two things are the projections of a common subgroup inside the direct sum, you get an isomorphism between C1 and C2. So this gives you 3 ways of embedding a chamorro variety for H, which is more or less a product of modular curves, into the Klingon level guy for G. So we get here something which is basically x naught of p times x naught of 1, because we're parameterizing 2 elliptic curves, no p level structure on the second one, and a subgroup in the first one. And the other way around, level structure in the second one. And here we get something fancier, which is, if you like, it's in between x naught of p times x naught of p, which just knows the CI, and x1 of p times x1 of p, which would have isomorphism between both of these things and the trivial object. So trivializations of both. And here we have something a little bit simpler. So XH delta is going to be the chamorro variety classifying this data. And it's the stuff whose reduction mod P is pairs of matrices in GL2ZP that are upper triangular and whose diagonal entries are the same. So just a little interpretation of where this is coming from. You can look at orbits of H on the flag variety for the Klingon, so G mod the Klingon, and there are 3 orbits of H on that flag variety. There's 2 closed ones, parameterizing lines which are inside one of the 2 subspaces, and there's this extra open orbit. And these open orbits really seem to be an important thing in studying decompositions of automorphic representations to subgroups and so on in lots of different contexts. And there's this map, which I'm going to call iota delta. And we can send the pair EI and CI to this abelian surface with the level structure C being the graph of alpha inside C1 times C2. So I've stressed this little piece of linear algebra quite carefully, just to emphasize that we've made a slightly non-obvious choice, and there is some theory behind why we've chosen it in this way. And there's a fiddly lemma, which is that if you look at the intersection of this guy with the greater than or equal to 1 locus, what you get is the locus where the EI are both ordinary and the CI are the canonical subgroups. Sorry, this is not quite true because this map, it's not obvious that this map's an embedding. So what I should have written was the pre-image of this locus inside XH delta. I beg your pardon. Subtle little point that. And yeah, you can actually rig things so these maps are closed embeddings. This is something we learned from Kai-Wen Lan, but this isn't actually needed, and it places much stronger constraints on the kinds of levels and cone decompositions and so on you can work with. So it's easiest just to use the fact that iota is finite and that the pre-image of this locus is this ordinary locus. So crucially, the image of iota delta misses, it has no intersection with the locus where C is multiplicative and A has P rank. Exactly one. So this is going to help us an awful lot, and the reason for that's going to become clear in the later on in these talks. And somehow this embedding is a little bit better than we might expect. It's obvious that the pre-image of the ordinary locus is the ordinary locus, but in fact, the pre-image of this slightly larger locus on G is still the ordinary locus on H. So we've got a map that kind of cuts across the stratifications in a slightly unexpected way. So these are spaces of p-adic modular forms. And it lands in H1 of XG Klingon and there's a and you can do this whenever L1 plus L2 equals K1 plus K2 minus 2. And with a little more work, you can show that these maps vary in families as well. So if you have some families of weights varying in a p-adic weight space, L1, L2, and K1 are allowed to vary. K2 remains fixed. That's because we're using this Klingon theory. But you can vary those three parameters as long as you promise to keep this equation satisfied. So that comes from promoting the map iota delta to something on an Igusa tower, so some tower of chamorro varieties parameterizing some trivialization of your subgroup mod p to the n. You can also see this in terms of the kind of big sheaves coming from nice loci and flag varieties that we saw at the end of Anson's talk earlier today. But yeah, that's needed if you want to allow things to vary in families. But at least in the simplest case, you get the push forward maps just directly from the fact that this pullback is equal to the ordinary locus. And so this embeds in here as a closed embedding. Well, its image is closed. So how are we going to use this? How am I for time? 15 minutes left. So if you remember this eta we had before, sorry, I've gone off the page again, haven't I? Thank you. So we had this eta, which initially was fairly arbitrary, but I'm now going to assume that it's an eigenvector for the transpose Klingon operator. So again, as we saw in Vincent's talk, you have these two algebras, two commutative subalgebras of the parahoric level Hecker algebra, one that kind of contracts stuff and one that expands stuff. So this is the transpose of the Euclidean that we used to define the ordinary projector above. And this means that the linear functional you get by pairing with eta, which is a linear functional on the H1, factors through the ordinary projector. Because, sorry, I should say it's an ordinary eigenvector. Yeah, so there's some ordinarity condition here. We want it to be an eigenvector for the transpose Euclidean operator with unit eigenvalue. And then because the two Hecker operators are interchanged by set duality, the linear functional given by pairing with this one factors through the Klingon Hecker operator for the usual Euclidean. So it makes sense to define p-adic L function, which I'm going to very roughly sketch. So this makes sense for specific holomorphic Eisenstein series EI, but the point is that it varies analytically as the EI vary. So what I'm using here is Katz's theory of the Eisenstein measure, which gives you p-adic families of Eisenstein series valued as p-adic modular forms. But we can go further than this. We can make sense of these push forwards eta F1 times F2 for Fi any families of p-adic modular forms. So we can take both of them, Eisenstein and you get a p-adic L function for pi, but you can also take one Eisenstein and one cuspidal. And then you get a p-adic L function for pi times sigma, where sigma is GL2 cuspidal, an automorphic representation generated by a GL2 cusp form. And you can also take both cuspidal and then you get some sort of period integral for non-holomorphic automorphic forms for GSp4 integrated against cusp forms on GL2 times GL2. And this should be a central value of a degree 16 L function for GSp4 and GL2 times GL2. And this is the global Gamgross-Prasad conjecture. So here you have a cycloatomic variable. You can look at different twists of the same object. So you're looking at the L function at different values of S. Here you're tied to the central value. And in fact, I'm lying slightly, it's the square root of the central value, if you believe the Ichino-Ikeda formulation of this conjecture. And the things you can vary are the weights of the GL2 cusp forms and also one component of the weight for GSp4. So you have some kind of variation in the Hida type family here. And this is known under some hypotheses. So if pi is lifted from GL2 over an imaginary or real quadratic field, then this conjecture is known. And I should mention that there is some complementary work of Bertolini, Cerveso, and Venerucci, which is also looking at these central values but they make a different set of assumptions on the weights. So we assume that the weights of the GSp4 thing are quite large, and these cusp forms have quite small weight. So in some sense, the GSp4 factor is dominant. Whereas the work of BSV is about the case where the GL2 guys have much larger weight, and the GSp4 thing is dominant. And there they use the H0 from pi and H1 from the GL2 factors. And there should be all sorts of other possibilities. So Sarah and I have a preprint that we've put up recently, which consists of an awful lot of conjectures and a rather smaller number of theorems about how you might go about interpolating these central values for all sorts of different ways in which the weights can intertwine, and how this relates with known or expected results on Gross-Prasad conjecture. Anyway, so that's just a list of things that you can use this construction, this push forward of pairs of modular forms projected to the ordinary part and then paired against eta. You can use that to stamp out several different kinds of interpolating objects, which are interesting for various kinds of p-adic L function constructions. And we think this sort of idea that you can relate higher Hida theory on different groups via push forward and pullback maps seems to have quite a lot of mileage in it, and seems to be useful for constructing p-adic L functions in quite a lot of other situations. So I think
I actually just want to make a remark there.
I was just about to say that I'm going to stop here for today and say a bit more about the details tomorrow. So maybe that's a good time to stop and hand over to Sarah for her remark.
But I just want to make a remark that Giada Grossi is working on using these ideas to construct the p-adic L function for quadratic Hilbert modular forms.
Indeed. So there are lots more constructions in the works that use various flavors of higher Hida and Coleman theory to construct p-adic L functions that weren't previously accessible, because somehow previous constructions relied a lot on using holomorphic or maybe anti-holomorphic automorphic forms and pairing those together. But thanks to the wonderful machinery of higher Coleman theory, we can now understand lots of other kinds of automorphic forms that contribute to cohomology in intermediate degrees, not just the bottom that you see with holomorphic stuff and the top that you see with anti-holomorphic stuff. So yeah, so I'll stop there, and I'll say a little bit more about the details of how these constructions work tomorrow. And then in the second talk tomorrow, Sarah will take over and explain the relation to Euler systems. That's all from me for today. Thank you.
Thanks, David, for this beautiful talk. Questions of remarks? Observations?
Maybe can I ask a question, David?
Please.
Yes. So I may already have asked this question, but so this form, like, so you take these two Eisenstein series. I mean, these two families of Eisenstein series.
Yeah.
Then they are pushed forward, and then we take this projector, and then but then we get a classical family in constant weight. Is that right?
Yes, that's correct.
So is there, is there some hope of constructing it directly? I mean, is there some, does it seem reasonable that one could construct this family directly? Because in the end, it's it's a family of classical forms of constant weight. So certainly not eigenforms, but okay. So I don't know.
Somehow I doubt it, because you can specialize the parameters at values where the Eisenstein series is not classical anymore. And then the projector gives you something, but it has no direct classical interpretation.
Mm-hmm.
That's a very important interpretation in terms of computing values of p-adic regulators. But I don't think there's any hope of constructing it directly on the whole tomorrow.
Mm-hmm.
You really need to construct it locally over this smaller locus, and use the projector to extend it.
Mm-hmm.
Maybe this question is related to what Vincent just asked, David. if your automorphic representation for the GSp4 factor is fixed, do you still need the full power of the higher Hida theory? Or the higher Coleman theory, whatever, I mean.
You certainly need something, because you need to be able to control, and if you tried to do this in a totally classical way, you could work with some kind of measure taking values in the direct limit of the cohomology of all the Klingon level chamorro varieties for Klingon mod p to the n levels.
Mm-hmm.
And you would need some way of controlling the somehow projecting that down to the bottom level and seeing how that interacts with the integral lattices.
Mm-hmm.
It doesn't seem to be possible to do that without really using the extra information that you get from the Hida. You can ask the same question actually for p-adic Rankin-Selberg L functions, for instance, and I really don't know of any sensible way of doing that either.
Mm-hmm.
Can you? I just wanted to make sure I understand. Why do you use Hida theory instead of overconvergent stuff? I mean, it seems that it should be easier to use overconvergent, but maybe you need something integral.
It's not so much that. I mean, higher Hida theory gives you control over integrality, which you wouldn't have in the Coleman world. But there's also a vital extra piece of information, which is the unit root splitting. Because if you take the Eisenstein measure, it has many specializations which are nearly holomorphic nearly holomorphic p-adic modular forms. Right. So they're the images of nearly holomorphic things under the unit root splitting. And that is really something that lives only over the ordinary locus. And it's something that it doesn't overconverge, as I think you know probably better than almost anybody else. And so what we needed to do to get this to work was to construct a sort of partial unit root splitting over the greater than or equal to 1 locus at Klingon level, where we actually used an old paper of yours, and then related that to the classical unit root splitting on the 2 factors of H. And this is really a structure that you only have in the world of Hida. So I actually asked after Fabrizio's talk whether there was any hope of doing nearly overconvergent families for GSp4 and interpolating powers of the differential operator, as you and Fabrizio did for GL2. But without having that, I don't think it would be possible to do the full strength of this construction in the Coleman world.
Right, I see.
And in particular, that's why we really need pi to be ordinary for the Klingon, not just small positives like for the Klingon.
Right, I see.
There is more questions, more observations?
Can I just ask something?
Antonio, hi.
Hi, David. So I understand pi has to be ordinary. What about the GL2 forms like sigma and in the triple product? Do you have to assume the eigenforms on GL2 are also ordinary?
Actually, no. Because what we push forward, I was a little bit sloppy about this. And what we push forward is actually the p depletions of the form. So we take the kind of maximally non-ordinary thing. And you can actually use this to get a bit more juice out of this construction. So I mentioned variation in Hida families, but you can actually do a little bit more in this GSp4 times GL2, or the self-dual and triple product construction. You can take the universal deformation with no local conditions of P. And you have a universal P depleted eigenform for that. And there you have somehow an extra variable that the Hida theory doesn't see, because you have one parameter ordinary Hida families. You have two-parameter nearly ordinary families where you have a cycloatomic twist as well. But the universal deformation ring is actually three-dimensional.
That's right.
So
Okay.
somehow the natural ordinarity condition here is that you have Klingon ordinarity for pi and no condition at all for the cusp forms when present.
Great. Thanks.
Okay. Let's say thanks again, David, for this nice talk. And